Straight line motion, what we call rectilinear motion. I'll write that in a second, but how many of you studied, not in this class because we've mentioned these before, but in other classes, position, velocity, acceleration? Raise your hand if you've done that. So maybe about half. And that's going to be helpful to you because we will use these a lot in this course, not just right now, but for this foreseeable future. And this particular lesson is a very important lesson in the year as a whole. So it's long. We have a lot to talk through. Hopefully we'll get through it today, but if not, we'll pick it up again. Please ask questions as soon as they come up. Yeah. Yeah. All right, write this, just those of you who go back and review your notes, which I recommend. Is it doing that again?
It does it every day. I don't know why he does it.
Well, because once it gets working, then it stays. Like my first 3 classes, I have 3 classes straight in a row. It doesn't do it after the first time. So I guess that must be the thing. It's a weird glitch. Hugely important. Now, we will use this maybe enough that you don't need to go back and review the details of it, but at least for the next few days or weeks, make sure that this is sticking. All right, first of all, position. That means where we are. Sometimes it's just going to be on a graph, like to the right, to the left, up or down. Maybe it will be more in context and more involved. Velocity, we know, is a directional speed, and then acceleration is how fast our velocity is changing. And I think everybody in here drives, am I right? So, no? Okay, most of you, but you've all ridden in a car or you've done something that accelerates, right? So if you use that as kind of an anchor concept, I think you'll be able to relate to this. Meaning, you're sitting at a light, you hit your accelerator, you start going faster, so your velocity is changing, potentially your acceleration is changing if you're moving your foot. When you brake, you're actually, in terms of physics definitions, you're actually accelerating when you brake, even though that's not what we say out there. No, we still say acceleration, and it's just a different sign. Okay, so all of that, just kind of think through driving in a car when you are thinking through this. First one, we're just throwing a ball up, okay? Just throwing a ball or throwing something and catching it. What is at work when we're throwing something and catching it?
Gravity?
All right, so we have an acceleration due to gravity. What else? What's making it go up if gravity is pulling it down? Okay, so yeah, the force of your hand, which translates into an initial velocity. Okay? And that's what's represented by this equation. I want you to know how to interpret. This is a position equation. I want you to know how to interpret this. And this is review from Algebra 2. So this first term is your acceleration due to gravity. If it's just free fall motion like this. Now, if I'm throwing something that has a motor and it's flying up, this is going to be a different number. But this is acceleration due to gravity. So it is negative because gravity obviously pulls it down. We'll talk sign in a second. And then the term in front of just t, that's your initial velocity. Again, sign matters. If this said negative 18, that means I threw it down. Okay? Which you might do if you're up high and you're throwing something down lower. And then the 2 is your initial height. Most things in physics and calculus will be done in the metric unit system. which is why it's negative 4.9. And then the negative 4.9 carries units of meters per second squared. So this is meters. So our initial height of 2 is meters, which is roughly our, like 6 feet-ish, a little bit higher. Okay. That is a standard format for any kind of tossed, thrown, kicked, launched kind of motion, okay? So just, it helps to understand what you're looking at. So this negative 4.9 is half the acceleration due to gravity. 18, we threw it up with an initial velocity of 18 meters per second, and then we threw it from 2 meters. So maybe like right here we released it. Or maybe it was over here. Make sense? Okay. All right, we have 3 graphs. If you've ever thrown or watched something be thrown, you know it follows this path, right? It's called a parabola, right? And it's cool because the actual math graph mirrors what it looks like when it flies through the air, at least somewhat. Okay, and then velocity. Why is that linear, number one, instead of quadratic like the first one? Yeah. Okay, so the negative acceleration is constantly working on our ball toss. And as it goes up, it's constantly slowing down. And then as it comes down, it's constantly speeding up, right? Yeah.
I guess a better way to say it is the slope of the velocity line is acceleration. The acceleration is linear slope.
Okay, did you say our acceleration is positive?
No.
He said constant.
Constant, okay, gotcha. All right, let's kind of make some connections. So note here we're starting at not 0, but just above, right? 2 meters. And our position is going to get higher and higher and then lower and lower back to the ground. So everything makes sense there. What is true right here at that point about the ball's motion? Say what you know.
It has 0 velocity. Highest point.
Highest point, 0 velocity. Those will go together. Okay? Note how that mirrors in the velocity graph. So our initial velocity is where the velocity was highest. At least, our velocity was most positive. Let's say it that way. Okay, we know the velocity keeps getting lower and lower until it hits 0. So that point and that point correspond. Roughly, what is that, like 1.9 seconds or so? Okay, and then it starts getting more and more negative, meaning it's speeding up, going back down to the ground. Okay? Everybody feel okay with that? Okay? Well, what's the slope of our velocity line? And I don't expect you to calculate it, but someone already said it was constant, right? So what kind of line is a constant slope? Or what kind of line, should I say, should we expect for the acceleration with this constant slope on the velocity graph? Yeah, horizontal line. Okay, so draw that one in. And it's down here at 9.8, but negative meters per second squared. And that's the acceleration due to gravity on Earth in metric units, or what we call SI. Have you guys heard SI for those units? Okay. So just take a moment to relate your 3 graphs. Quadratic, linear, constant. Everybody good on those? Okay. Well, once we write this next section, you're going to see why that is. So first of all, position is S. S of t, not P of t. Or sometimes you'll be given it differently as X of t, but the standard is S. Those of you who've taken physics, do you remember that? And you're kind of like, why? But okay, velocity. Well, velocity is the first derivative of position. Okay, thinking of the fact that maybe you already knew that, but now we're talking calculus, right? So we're saying the word derivative in here. Well, if I take this, let's just simplify the equation. It was this whole thing. But if we ignore some of the details and we just take the derivative of negative t squared, what is it? Negative 2t, which is a downhill line, right? Okay, what's the derivative of negative 2t? Negative 2. There's our horizontal line, okay? So I kind of just told you, but here's acceleration is v prime of t. So take the derivative of velocity, and that is acceleration. Or what else could we write here?
The second derivative of s.
Yeah, s double prime of t. So first thing to point out there, be careful that you don't just assume every second derivative is acceleration. Like we wrote, this is a first derivative and it's an acceleration as well. So you have to be careful what it's a derivative of. Okay? I guess before we continue, I should have had you do this a second ago. But anytime you take a derivative, they are rates of change. So something per something, right? Like we have to have a double name unit, rates of change, like miles per hour. Sorry that it's not fitting on there. There we go. Bet you it's zoomed in. No. All right. Okay, now we're going to talk motion. And you heard me saying as the ball goes up, it's positive. As it comes down, it's negative, that kind of thing. Well, we have what we call sign standards, and so that's what we're about to write. What does this first one say? V of t, this symbol 0. What does that mean? How would you read that just in English? Yep. The velocity is less than 0 or negative, right? If it's negative, the particle is moving left. Or it's moving down, depending on which direction we're talking about. So left and down, think quadrants in a 4-quadrant graph. Like quadrants 2 and 3, that's left. Those are both negative x. Quadrants 3 and 4, down. Those are both negative y. All right, v of t positive, that means it's doing the opposite. So that's up, well, right or up. Okay, how about 0? What's it doing in that case? Yeah, not moving. Our word for that is at rest. Our words for that. Okay, if you want, you could make a quick little sketch of this, like this is negative and negative, and this is positive, going this way and this way. Let's see if I can fit that. Just as a visual, if you're more of a visual person. Any questions on that? That's going to be important because you'll have to read carefully, like sign of velocity versus sign of acceleration, and know which way we're moving. So everybody good on that part? Okay. All right, average velocity. Let's see if you can tell me this. Velocity is a rate of change. So this is basically saying average rate of change of particle motion, right? So what is our formula for average rate of change? You guys remember? In fact, you could just remind yourself average rate of change. Anybody remember?
Isn't it just like the slope?
But how do we calculate it? Like, how does this look in calculus? That's algebra 1. Calculus. How does it look in calculus?
F of A minus F of B over A minus B.
That's better, yeah. But we're talking about velocity, so we'll use S since it's our position. Good. And usually we use B as the second point. So S of B minus S of A over B minus A. Put a box around that just so you have it. We don't do a ton with it, but sometimes the question comes up, like, what's the average velocity on this interval? And then you have to like zoom out of calculus and back to just calculating a slope, which you said that, and that was true. All right, speed is the absolute value of the velocity. Which does what to it? It essentially removes the sign, right? So speed is directionless. That's all. I guess we could just say it that way. So if you're walking at 5 miles an hour, that's pretty fast. 12-minute mile walking, that would be pretty fast. Jogging at 5 miles an hour. Basically what we're saying here is the direction you're going doesn't matter. So you're jogging that direct, like 5 miles an hour headed home versus headed here versus headed to lunch. Like, it doesn't matter. It's just 5, okay? So I think that's probably good enough. Is everybody good with the word directionless? Does that make sense to you? Okay. All right. I'm putting stars by this. This is going to be another example of when we have a question that asks us to justify. So thinking FRQ, and you have to actually write out words, and they look for specific phrases. In your last one, does anybody remember meaning section 4.1? What was the phrase that we had to learn? At a rate of. That was our big phrase. Okay? So we'll have one for this too. It's kind of here already. So what do you think? If velocity and acceleration have the same sign, the particle is what? And you're choosing between speeding up or slowing down. Yeah. So let's use the car, driving in a car analogy. You're driving down the road. Let's say we're going towards town, towards Grand Junction. So we're headed west. And you hit your gas to speed up, to pass somebody maybe. So we just said speed up because when you hit your gas, it's accelerating you in the same direction that you are driving, right? Which would be west. What happens when you hit your brake? Which way are you accelerating? You're accelerating east, right? So what happens to your speed? It slows down. Okay, so when those are in opposition, you're slowing down. When they're helping each other, you could think of it as they're speeding up. So we know now we can say slowing down here. And the phrase is this first part. Velocity and acceleration have the same sign versus velocity and acceleration have different signs. So with these stars, I'm going to say key phrases for justification. So let's go through this table. What is the t negative 5? What does that mean? Yep. 5 seconds ago, maybe. Okay, and then velocity is 3, acceleration is -4. So is it speeding up or slowing down? Okay. If I said justify, what would you say?
Velocity and acceleration.
Yeah. At time t equals -5, the particle is slowing down because velocity and acceleration have different sign. Okay? How about the second one? Slowing down or speeding up? Yeah, slowing down. At time t equals 1. What? I was still doing that one. Yeah. Manning, finish the sentence. At time t equals 1, the particle is
Slowing down because velocity and acceleration have different signs.
perfect. Chloe, tell us about the third one. At time what? The third one. Say the whole sentence. At time. We're here.
Yeah. At 2 seconds.
Okay.
It is
It is speeding up. Why? Help her out, Sonia. Because velocity and acceleration have the same sign? Everybody good? Notice we haven't said a word about the numbers, right? Like we don't even care about the differential between them, like the fact that -4 and 3 or 7 and negative, like we haven't said any word about that. It's just, do they have the same sign or not? So we're not worried about how fast it's happening, just if it's happening. Make sense? All right, last one. What's going on there? Speeding up again. Which direction? Left for the last one. Okay, we're already headed negative. Now we're accelerating negative, so we're speeding up negative. Guys, this first part of this lesson is not much example and a lot of concept. So how you doing? Feel like you're following okay? Okay. Hey, I like that. Hang loose. All right, displacement. I don't really like how it's jammed up against that. If you studied physics, displacement can mean more than just this. Like when you sit yourself, well, I don't know if anybody takes a bath, but if you put you in a bathtub or you stick something in water, what happens to the water? It gets displaced, right? But that's not this displacement. This is net. Yeah, this is the definition. Net change in position. Please subtitle or subscript this. It is not distance.
It's not distance.
Meaning, well, let's ask Sonia. She's a runner.
Yes.
Let's say this is Sonia's race course. I don't know. This is Lincoln Park. It is today. You start over here on hole 1 and you, right? Do you run the golf course holes?
Yeah.
And then you head off to, anyway. Okay, this is the start. Maybe I shouldn't have picked on her. Okay, in a race like this, they run around and they end back where they started. What's the displacement?
0.
It's 0. If you run, even if you run 30 miles, you end up back where you started, your displacement is 0. Okay? Because we're not talking distance, we're talking about how far from the beginning are you. Make sense? How far from the start?
Is that like absolute value? 27 miles, is there different,
Okay.
displacement 27, or is it negative?
Let's say you run and you end up here, and this is a little bit hard to do with where I put the starting line. So let me maybe move the starting line. And I'm not going to consult the expert because I'll probably do it wrong anyway.
I can draw it for you if you want.
Yeah, that's okay.
Oh, dude.
Okay. So thinking left, right, positive, well, negative, positive. If you, to answer a writer's question, if you ran around and you stopped right here, your displacement would be like positive whatever distance, like positive half mile or something, right? But if you stopped on the other side, now your displacement would be negative 1/2 mile or however far. Okay.
It's like an x displacement and a y displacement.
Well, in this kind of context, yes, but a lot of these problems will just be one directional.
Oh, okay.
Yeah, not both.
So it's a progress displacement?
Oh, what?
Progress displacement? You're this far along the track.
Yeah. Yeah, I guess you could think of it that way. It'll make more sense when we do an actual example. But basically, the idea is how far are you from where you or the particle, how far is it from where it started? And that's your displacement. Let's do a quick, easy one. Just because this can kind of get a little bit confusing. So let's talk about a particle, our favorite boring little thing. Moves left 200 and then right 75. What's its displacement?
Do you want to say it too?
Yeah, I do.
Negative 125.
Yep, negative 125. I'm going to tell you this as we do the example, but let's write it right here because this is where you're going to probably see it. It is x final minus x initial. In terms of calculating, if you're given like an equation for its motion, that's what you would use. So final minus initial. Does sign matter? Like what if you did initial minus final? It matters, right? For sure. You'd get the wrong sign. All right. Questions on the concepts? That's a lot there, right? You might want to go review that section before tomorrow. So we're given this equation of motion. Notice that that this time it's given as x of t instead of s of t. But this is just one directional motion. So it's moving along the x-axis only. How often does that happen? Not in my world. I'm serious. Like most of the time things are moving in 3 dimensions, right? So this is a very simplified analysis, right? Okay. Find the displacement of the particle during the first 2 minutes. Before I actually read that, it is important to note the units. So we're dealing with centimeters and minutes. And sometimes it might even be helpful, especially if you're doing an FRQ, to make that note. Because if you put the wrong units, man, you've done some work and lost points, right? So centimeters and minutes here. All right, find the displacement during the first 2 minutes. That would be x of 2 minus x of 0. What is x of 2? Well, that's going to be 8. So 2 cubed minus 4 times 4 plus 3. So negative 8 minus 16, negative 8 plus 3, that's negative 5. X of 0, that one's easy. It's just 3. Everybody see where I got those? Just plugging them back into the function. So our displacement is negative 5 minus 3, which equals negative 8. What does that mean the particle did? If you had to describe it, what would you say? Left 8 units from the beginning, right? Okay. Notice the beginning wasn't 0. Where was the beginning?
2, 3.
At 3. So that was technically the starting point. All right, find the average velocity. What is average velocity again?
V prime S.
Nope. Holy moly, you guys. I am going to have a stroke if we cannot get the difference between instantaneous and average.
S of 8 minus S of over B minus S.
Okay. S of 2 minus S of 0. Oh, I shouldn't be using S. I should be using X. Did you set me up to do that?
Sorry.
All right, we already know X of 2 and 0, actually. So negative 5 minus 3 over 2. So this is negative 4. Is it okay to leave it as negative 4?
No. We'll have to use
You have to what?
Label it.
Label it? Label it what? Centimeters per minute. By the way, I should have done that on this negative 8. So, what is the units for our displacement? Just centimeters, right? Okay. How far are we from our start? Well, that's when you say how far, that's like a length, so centimeters in this case. All right, find the velocity of the particle. Velocity is what? First derivative of our position. So that is x prime of t. And what is x prime of this particular function?
3t squared minus 8t.
Okay. So make sure your notation is all sound. Like all I did there was calculate the derivative. So it was x prime of t. Now we're going to say x prime of 4. So that's now substitutable. And so 3 times 16 is 48, minus 32 is 16. What do we label that?
Centimeters per minute squared.
Nope.
Oh, wait.
Centimeters just per minute still, right? Guys, what's the difference between the units of average velocity and the units of instantaneous?
They're the same.
They're the same, right? It's still a velocity. We're just saying, think about your idea of maybe our particle is speeding up, slowing down. Well, moving around differently. Average is like that versus instantaneous right at the point. Okay? So between 2 points versus at a single point in time. All right, acceleration. Acceleration is what? Okay, so you could either say v prime, right? So it's v prime of t. That's what I'm going to write. Or you could say it's the second derivative of x and do it that way. But since we just did the derivative of x, why don't we just take the derivative of the velocity? which is what?
16 minus 8.
16 minus 8. Okay, now we come over and say a prime of 4, and that is 6 times 4 minus 8, which is 16. That is not a common thing. That's a coincidence that they're the same, so don't try to see a pattern in that. What are the units of acceleration?
Centimeters per minute squared.
Yeah, centimeters per minute, and you can stick a little 2 there. Or you can say 16 centimeters per minute, and that's also okay. That's more of the conceptual idea. Like, so every minute we're gaining 16 centimeters per minute in our velocity. Okay, note the word justify in this one. Sometimes, or maybe very often, it's nice to start with your justification. So, what is the justification? Like, when do we know, or how do we know something is speeding up? Okay.
And the acceleration have the same.
Okay. So, in this case, is it speeding up or slowing down? Why did you say slowing down?
He said slow. You should recognize my voice by now. It's the most
Because why? So speeding up because? Okay. We don't have time to do the graph. All right, why don't you circle the following problems for tonight? One, two, three, 6. Try number 7.
Let's go.
Oh my gosh. I swear. 9 and I guess 9 has 2 parts, so 3 parts. We'll come back to those graphs and probably hopefully have time to do those in class tomorrow.